Hello, good afternoon. Share the screen with the students that are online. Okay, so it's time to get started. Any questions about the topics that we covered last week on Monday and Wednesday? So we started this topic last week on flow and activity relationships, and we're going to continue the discussion this afternoon. Today we're going to have also a lab assignment. So if you are in your computer, you'll see that there's a link for a lab for today. But we're going to, again, work in class and discuss the details and the solution. So let's get started. And we started the discussion of this lecture. I think we covered some of the slides last time, but now we're going to be focusing on the activity relationships and the space requirements. And we want to make sure that we understand the flow between these departments inside the facility. The idea is to be able to somehow quantify this quantitatively or qualitatively using some of the tools that we are going to discuss in this lecture. So from a quantitative way, we're going to make sure that we use a baseline, meaning that we have the same measure that quantify the units for all departments in the same way. In using qualitative ways, we're going to have some standards that are going to help us identify or rank the amount of flow that is happening between departments. So let's look at those ideas and those methods today. Again, the learning objectives for this lecture is to understand the interactions between flow systems, flow or activity relationships, and space requirements. I think those blocks are not working. Last time I checked, they were not working. So you have to move to one of these tables. Yes. Obviously, as they relate to facilities planning. So let's look at the activity relationships. And again, I think we touched on this last time. We want to measure the activities among departments. This is one of the most important elements in the layout for new facilities and the layout of departments. So we want to understand how things are moving, how often, and which departments have the highest interaction and the lowest interaction in the same way. So we can evaluate different locations for these departments and then assign locations and then build our facility layout. To evaluate the alternative arrangements, we have activity relationships. And the activity relationship may be specified in a quantitative or qualitative manner. So we discussed this example. This is what is called a mileage chart. And again, it's quantifying in terms of the number of miles between cities, how far are located from this group of 8. So we have the distance among them. And obviously we have an empty diagonal line here because that corresponds to each one of the cities. But we can easily find what is the distance from Atlanta to San Francisco. And it should be the same as San Francisco to Atlanta. So this is the same number as you're seeing here. And the idea is, okay, we can look at these numbers and see, okay, if we are gonna place we look at all the numbers, we look at San Francisco is the one that is located the farthest from most of them. With the exception, we'll say all of them are over 2,000 with the exception of Dallas, Texas. So those are things to consider. Maybe Dallas is a good location if you have a high volume of things being moved to San Francisco. So those are the things that we want to start studying. So when the distances are symmetric, we can represent the mileage chart using a triangular mileage chart. And I show you how this is done. So you place, again, this is under the assumption that the distances are symmetric. So you go from one point to the other, and the distance is the same from going backwards. So that's symmetric. And if you have something like that, then we can build this type of graph in which you place all the locations, and then the distance will be in the intersection between the two cities. And then quantifying the flow measurements. Flow may be measured quantitatively in terms of the amount moved between departments. So now going back into the facility, the chart most often used to record these flows is the front two chart. So here we have a number of departments. I think there are 7. And we have those 7 departments also listed at the top. And we are looking at the amount of flow between these departments. So from stores to miling, you have 12. That's the volume. If we look backwards from miling to stores, there's nothing, right? So there's only movement in one direction. And that's why these two triangles are not the same, right? Because movement from stores to miling doesn't necessarily mean that you have movement going backwards. So we are quantifying the movement, forward movement, backward movement into these areas. And that's what we do when we build these front two charts. So these are the steps for constructing a front two chart. We're gonna list all departments down the row and across the column following the overall flow pattern. And then we're gonna establish a measure of flow for the facility that accurately indicates equivalent flow volumes. So I mentioned this several times. We have to find that equivalent measurement that is going to be used in order for us to be consistent with the amount of flow that is happening between the departments. I presented the example. It's not the same thing of moving a lot of boxes or a pallet of boxes. I'm just moving a single box. So even though it's the same, just one movement, the amount that you're moving is different. So we have to find an equivalent measurement. So if we're going to use boxes, then everybody's going to be measured using boxes and so on. So if the item moves are equivalent with respect to easy of movement, the number of trips may be recorded in the front two chart. If the item move vary in size, weight, value, shape, and so on, then some common unit of measure may be established so that the quantities recorded in the front two chart represent the proper relationships. And the lab that we're gonna be working this afternoon is gonna be looking at that. We're gonna have to start by looking at finding a common way of measuring the flow. And then once we find that common measurement, we're gonna build the front two chart. Based on the flow paths for the items to be moved and the established measurement of flow or measure of flow, record the flow volumes in the front to show. So very simple. I will say that challenging part is this bullet right here. If you don't have the same amount of movement or the same item is being moved across the facility and you have to find this common denominator in order to measure the flow, then that's what the challenge is. Once you have that information in the right amounts, the rest is very simple. So here we have an example. So in this example, we have a firm that produces 3 components. Component 1 and 2 have the same size and weight and are equivalent with respect to movement. So they have the same size and the weight is equivalent. Component 3 is almost twice as large, and moving 2 units of either component, 1 or 2, is equivalent to moving 1 unit of component 3. Thus, a movement factor of 2 is assigned to component 3. The departments included in the facility are named A, B, C, D, and E. Okay, so these are the 5 letters that we're using to identify these 5 departments. For this illustration, we assume that the departments are arranged in a linear flow pattern in the order A, C, B, D, and E. Okay, so these are aligned in a series, A, C, B, D, and E. The quantities to be produced and the components routing are as follows. So we have in this table, for each component, component 1, 2, and 3, we have the production quantities per day, the movement factor. So you see for 1 and 2, it's just 1 unit. For component 3 is twice, because we know it's twice the size or twice as large when compared to components 1 and 2. So if we look at the production quantities and the equivalent flows per day, component 1 has 30, component number 2, 12, and component number 3, 14. And we have the routings. So what we're gonna do is we're gonna look at these routings and we're gonna try to come up with the amount that is being moved between departments based on the routings of each product or each component. Okay, so we can start with, let's say, component number 1. And we have a routing that starts in A and then goes to C. Right, so we're gonna be moving 30. So 30 units being moved from A to C. So I'm gonna differentiate this with number 1 that corresponds to component number 1. And I can say, okay, from A to C, based on this first part of the routing, there's gonna be movement from A to C, and we're gonna move 30 units of type 1. Then we look at the next one. This is C to B. And again, we are moving 30. So from C to B, are also moving 30 units, right? So this is C and this is B. And we continue this process from B to D, 30 units. So B is here to D. We are also moving 30. And from D to E, we are also moving 30. So D to E, sorry. We're also moving 30 units. And that's for the first component. Now let's look at the next one. So component 2, moving 12 units a day based on the conversion. And we're gonna start from A to B. So from A to B, we have 12. From B to D, we also have 12. And from D to E, we have 12. And then the last one, is component 3. Equivalent flow is 14 because even though we only moved 7, they're twice as big. So we're gonna use that conversion. So it's gonna be 14. And we go from A to C, 3, 14. C to D, 14. D to B, so also 14. And B to E, so also 14. Okay, so those are the total flows. So now I need to add those that are, if we have products of different types that are happening between these departments, we have to add them up. So I'm gonna change this color. So in total here, we're gonna have 44. That goes from A to C. This is gonna be 12. It's gonna be 30. It's gonna be 14. This is gonna be 14. This is gonna be 42. 14 and 42. So our front two chart is showing a total flow from A to C of 44, A to B of 12, C to B 30, C to D 14, B to D 42, B to E 14, D to B 14, and D to E 42. Okay, simple. Again, very simple, but the idea, or I think the most challenging is to find this movement factor. Okay, so along those lines, then we're gonna start working on that lab that is posted. So I'm gonna open the problem. You're gonna see it on the screen now, and you're gonna use a piece of paper and try to solve that one. And we are gonna discuss it here in class. So let me share that.
So, Professor, this from to chart, like in this sense, is just to understand the traffic between different machines?
Between different departments. So this
Okay.
will be something you have, in this case, you have a facility that looks like this. You have A, C, B, D, and E, and these are departments. So you can have different type of machines inside of each one of these departments, and you're trying to measure the amount of flow that is happening between these 5 departments.
Gotcha. Thank
Okay,
you.
good. So let me share. So this is the problem. We have paper flow to be expected through one section of City Hall consists of the following. 10 medical records per day from records to marriage licenses, 7 certificates per day from printing to marriage licenses. These are names of departments, so records, marriage license, printing, marriage license to lab, 6 blood sample reports per day from lab to marriage licenses, and 1 box of medical records per week from marriage license to records. I'm giving you some information here about the size of each one of these products or records that we are going to be moving. So 1 medical record is equivalent to 1 certificate. 1 medical record is equivalent to 1/2 of a blood sample. 1 medical record is equivalent to 1 blood sample report, and 1 medical record is equivalent to 1/10 of a box of medical records. So using these conversions, we want to develop a front-to chart for this section of City Hall based on 5 working days. Okay, so let's try to see if we can get those conversions and then try to build the front-to chart. And I'm going to copy this into PowerPoint so we can write. I cannot write in the PDF. So let's do that. Print screen. Just 1 minute. And we are going to assume that this is a 5-week business type of environment. So work from Mondays to Fridays. The last one, it says, is 1 box of medical records per week. Yes. So that's what I wrote there in red is just the information that we have from the description. And now based on that, we have to build this equivalent measurement. So for example, 51 medical record is equivalent to 1 certificate. So in the medical records is the unit, right? The common measurement that we are using. So 50 means, since it's the common measurement, it's gonna be the same. We're gonna be moving 50 records. So the equivalent loads per week is gonna be the same, 50, because that's the unit that we are using as a common unit measurement. And we know that 1 medical record is equivalent to 1 certificate. So that means that we have 35 also here. And then we move to medical record is equivalent to 1/2 of a blood sample. So So 1 blood sample to be equal to 2 times the number of medical records. So this will be 60. Does that make sense? So 1 medical record is equivalent to 1 blood sample report. So that stays the same. And 1 medical record is equivalent to 1/10 of a box of medical records. So medical record equals 1/10 of the box. So 10 times medical records equals 1 box. So this is gonna be 10 times 1. It's gonna be 10. So those are the equivalent loads per week. And now using this measurement or these volumes, we can build the frontal charts. I'm gonna rewrite this in here. So medical records equals 1/2 of a blood sample. 1 blood sample equals to medical records. And then medical records equals 1/10 of the box. So 1 box equals 10 medical records. So this is used here. This one is used here. So this is my from-to chart. From records to merit license, we have 50. From printing to merit license, we have 35. From merit license to lab, we have 60. From blood sample, from lab to merit license, we have 30. And from ML to records, we have 10. Is it right? No. And from lab to ML. Thank you. $15 and $60, $35 and $30. The rest is 0. And that's the flow from-to chart for this particular case. So you see the process, set up the components, the routings, Routings are going to tell you where the departments, what type of flow is happening. And then we have a quantity per week. So we have to find an equivalent measurement. In this case, we have the data stated in terms of the medical records. So that's our unit of our common unit of measurement. And we use that to find the equivalent loads per week. So after we get that information, then we can proceed to build the front-to chart. In this case, you see that there's some departments have very high interaction. 16. There's this one too. So looks like marriage licenses is one of those areas that is requiring a lot of flow. So we have to make sure that if you're grouping or locating departments, you pay attention to that particular department and their interaction with records and also labs. Okay, so again, we are just gathering data at this phase. We're getting all this information, we're learning tools, and we're gonna use this information to start building our layouts. And that's what we're gonna be doing next. Any questions? So this is from a quantitative point of view. Now we are gonna look at a strategy that is from a qualitative point of view. And remember, this is your third lab, so make sure that you submit this before the end of the day today. So here's the activity relationships in terms of qualitative flow measurements. So flow may be measured qualitative using the closeness relationship values developed by Mother and given in table 1. So these are, there's another way. If you cannot gather information from the floor, or maybe you're building a new facility and you don't have that information, we can always gather information through interviews or from people with experience working in similar facilities or similar industries in order to understand what will be the best way to locate these departments inside a facility. So this is a strategy, again, Dr. Mother developed this. This is called the closeness relationship values. And we have a scheme that uses these 6 letters. A means that the closeness between departments is absolutely necessary. E is a lower level, means that it's especially important. I is used for important, O for ordinary closeness, okay. U, unimportant, and then X, meaning that is undesirable. The difference between these two, with an X, you need to make sure that those 2 departments are not close to each other. Right? That's the meaning of X. With a U, you can put them together or you can't. Really matter, okay? But with this one, you have to make sure that those 2 departments are far from each other. For example, there could be some type of chemical gases that are happening in one department, and you want to make sure that that one is located far away from areas where you have a lot of people or a flow of people. So those type of things. So we're going to look at this information, see how can we use this. These values or the values may be recorded in conjunction with the reasons or the closeness value using the following relationship chart. So this looks like the mileage chart that we discussed at the beginning of today's lecture. Now we are using it from a qualitative point of view, in which we are having departments being listed on the left side of the chart, of the relationship chart. And then each diamond is gonna have two pieces of information now. It will have information about the type of importance between the relationship of those two areas. And also it will provide a reason. And here's a list of codes that we can use for list the reason why we are given that specific ranking to the relationships. So it could be based on frequency of use high, frequencies of use medium, frequencies of use low, information flow high, information flow medium, information flow low. And these are just examples. You can come up with a different guide of codes that you can use for reasons. The idea is that you don't fill out this information with words. You just have those codes listed inside the chart. So when you look at the relationship between those two, you can go straight to the codes, and then you can find out what that represents. So again, for directors, rooms, conference room, and the president, you have an important value. The reason why is because of the frequency of use is very high. Do we have an A here somewhere? I cannot see it. 25 and 6. Yeah, there's one here and these two. So plant manager and plant engineering office, absolutely necessary. The reason is because the type of information flow is very high. We have an X. Let's see an X here. In this case, there's no X, but there's unimportant and O's, I's, and E's. I think they're listed. So this is one example. And again, we can use this relationship chart to illustrate not only the value of closeness based on this ranking, but also the reason why. And this is useful, again, when you're dealing with a company that you might not be able to gather information, like quantifiable information. This type of chart will be useful. You just have to interview people, have to gather the data from another perspective, gathering information from maybe the users, maybe from the plant manager, the personnel, the staff, and then using that information, you can come up with this type of ranking. Qualitative flow measurement, difference between relationship values U, unimportant, and X. I think I mentioned this already. Two departments can be placed adjacent to each other with a relationship value U. Two departments cannot be placed adjacent to each other with a relationship value X. This could be because there's some environmental, safety, or facility constraints that are keeping you away from putting those two together. A relationship chart may be constructed as follows. So this is, again, a relationship chart. So how to build that? We list all the departments on the relationship chart. So those are the lists that you have in the first column. And then we conduct interviews or surveys with persons from each department listed on the relationship chart and with the management responsible for all departments. Again, the idea with this tool is that you go, you talk to the people that are familiar with the area, and they tell you based on experience, this is what's going on. We need to have this department close to each other because we are doing X, Y, Z. We don't want this department close because this is going to avoid or is going to contaminate this X, Y, Z. So you get all this information. This is an extensive process. It can take a long time. Okay, so we want to make sure that we get all the information that is going to help us make the rankings. Then we define the criteria for assigning closeness relationship and itemize and record the criteria as the reasons for relationship values on the relationship chart. So for instance, these two tables, we get this. Now we have to come up with these reasons. And then you can also have some type of ranking or trade-off analysis that you say, okay, if I'm giving it an E, then I have to make sure that I select reasons 2 or 5, for example. For an E, you have to have this type of reasoning. and so on. You can come up with those guidelines so you keep the consistency with the evaluation. Establish the relationship value and the reason for the value of all pairs of departments, and allow everyone having an input to the development of the relationship chart an opportunity to evaluate and discuss changes in the chart. So after you complete this exercise, you're not done. You have to show this to the people involved, make sure that you get the feedback. Maybe some additional information is going to come up with those meetings, and you can include that information into revising the chart. Remember that these decisions are long-term decisions, right? When you're building a facility, when you're designing a facility, you're making decisions that are going to be there for long-term. So we don't want to miss any important information when we are making this decision. So feedback, interactions, an iterative process happening between the evaluators, the people that are designing, the people that are working in the facility, and so on. Any questions? Good. So let's talk about space relationships. Yes, sir.
I think it's also important to consider possible future changes and anticipating those in a design.
Yes, correct. So, and that's what we mentioned in one of the lectures last week, I think, or before that, including this market forecast, understanding what are the things that can happen in the future, all those things are relevant and important. Are we going to expand? Are we thinking about adding new products and so on? So those things, yeah, you're right, are important when we are evaluating all these options. So space relationships. The most difficult determination in facilities planning is the amount of space required in the facility. Obviously, you know, facility, larger the facility, more expensive it is, right? Because not only the space, you have to use all this equipment to cool the facility, heat the facility, and so on. So the facilities planner then has the difficult task of projecting true space requirements for the uncertain future. And this connects with the comment that we just received from one of the students in the Zoom. Okay, so we don't know what's going to happen in the future, but we as facilities planner, then we have to have we have the difficult task of projecting what will be the space requirements for the future. In manufacturing and office environments, space requirements should be determined first for individual workstations. Departmental requirements should be determined based on the collections of workstations in the department. Okay, so there's this hierarchical process that we have to go through. Most of the time, you already have if there's a company that is looking for expansion, you know what type of process you're bringing into the facility. Those designs for workstations are already in place. So you will know from building a facility for X product, I will need this many departments, and these are the type of workstations that I will have inside the department. But everything starts with considering the amount of workstations that you're gonna need, number of machines, number of benches, number of tables that you're gonna need inside each department. Then you come up with the design for the department. You do that for every department in the facility. And then we look into generating the layout for the overall facility. So last point here is saying just that. Departmental requirements should be determined based on the collection of workstations in the department. So when we talk about workstations, that includes space for equipment, materials, and personnel. And this is just an example. So you don't only have space for the operator of the machine, you need space for the machine, you need space for the materials, incoming materials, in-process materials, and maybe for storage, the final product. So all those things that has to be in consideration, okay? And maybe a single station with a single machine, like this one can become a department, or maybe you need multiple workstations like this one inside a department. Again, it will depend on the type of product, type of process that you're running in your facility. But everything starts with the design of the workstation. Once you have come up with that design, you know the dimensions, you can build the design of the department, and then we can go proceed with the same type of process for each department in the facility, then build the overall requirements for space, and then look at the design of where to locate these departments using the information that we already discussed at the beginning of this lecture, flow measurements and so on. So once the space requirements for workstations are determined, the space requirements for each department can be established. Ensure that operational interferences are not created by simply combining areas needed by individual workstations. Additional space is required within each department for material handling within the department. So if you're going to be using forklifts to move material from one department to the other, you need to make sure that you have enough space for the aisles. If you're going to be using a conveyor, if you're going to be using an AGV or some type of material handling equipment, you have to take into account that space. So here's some aisle allowances estimates that we can use. So if the largest load is less than 6 feet square, then the aisle allowance percentage should be 5 to 10% of the total area of the department. As you move and you go this, if you have largest load, you know that the percentage is going to be increasing according to that. So aisles, very important. You have to make sure that you design for that space so you are able to move your product within the departments and the facility. Okay, so that's the last slide for this part. We still have some time, so we're gonna look at the next part, which is layout planning model. So now we're gonna start looking at location of departments within the facility using the information that we just learned. And there's gonna be some design algorithms that we're gonna be learning. Okay, so there are different strategies that we can use to come up with a design for a facility in terms of the layout. And I'm gonna be discussing those in this lecture and the next one. So there's several, you know, look at each one individually and discuss the benefits and disadvantages of each one of them. So again, these are the objectives. So we've talked about those already. Make sure that at the end of the semester, you are aware of, you learn these things. We are gonna be looking at some of these objectives today, like number 2, learn formulation models and analytical procedures for the study of facilities layout plan. So in the agenda, we have these topics, basic layout types, layout procedures, and then algorithm approaches. So I think we can look at the first 2 today and then continue on Wednesday. In terms of learning objectives, we're gonna look again at layout planning models and design algorithms for the development of layouts for the facility. Okay, so again, we have some information, some basic information now about what are the things that are relevant when we are trying to design a facility layout. Now we're gonna try to use that basic knowledge to apply that information to solve an actual problem, to find design alternatives for the facility, given some constraints. So the generation of layout alternatives is a critical step in the facility planning process. The layout selector will serve to establish the physical relationship between activities. So most of the facility layouts can be viewed at 2 levels. The first one is the block layout, which shows the location, shape, and size of each planning department. Second one is the detail layout, which shows the exact location of all equipment, workbenches, and storage areas within the department. Our focus in this class is primarily on the quantitative methods for developing and evaluating alternative block layouts. So once you understand the size, the space that you're gonna need for each department, then we're going to try to find the best way to allocate those needs within a specified space for the facility. So what are the basic layout types? In lecture 2, we identified 4 types of planning departments. If you remember, those are fixed material location departments, production line departments, product family departments, and process department. And we have this chart or figure that show, okay, when to use production line department versus process department. We have 2 ways of identifying when. You look at the volume of the type of products that you're producing, and so on. So based on those amounts, we were able to say, okay, so based on this volume, we are going to be using a process department. So make sure that you look at that graph, and then identifying the right number and the type of departments that are going to be used to populate the layout is a key step of the facilities planner must perform first. Okay, so we need to identify the right number and the type of departments based on these 4 type of departments that are going to be used to populate the layout. So let's start with looking at the different layout procedures. Different procedures have been developed to aid the facilities planning in developing layout alternatives, and they can be classified into 2 main categories: the construction type and the improvement type. So the construction type basically assumes that you're going to start from scratch. This is not something that is not currently in place, not existent. So we're going to build this from scratch. And the improvement type is going to look at improving the current design of a facility. So construction layout methods basically involve developing a new layout from scratch. Improvement procedures, on the other hand, generate layout alternatives by seeking improvement in an existing layout. So when we build this facility, we went through that process. Okay, we went through understanding what were the needs, the flow that we were expecting in each floor, what were the requirements for each program, and we did a construction method, basically build the facility from scratch. And then on the other hand, RFM went through an improvement procedure. So there were some existing layout, and now we have this space that we are going to redesign to accommodate new needs. For example, bringing the civil engineering program. So existing facilities, labs, classrooms were redesigned to accommodate those needs. So those are examples. There's layout procedures. They are similar, but they, from company to company, they're gonna have some specific steps. Like for example, here, there's the Apple's plan layout procedure. And we're gonna just scan through it, but it requires some typical steps, like gathering the data that is needed, just like we did in the previous lecture, to plan the material flow pattern, consider the general material handling plan, calculate the equipment requirement, and then we go through the process, the hierarchical design, going from workstation to the actual layout. So this in terms of specific company. And then we have the REITs plan layout procedure. This is more theoretical. And you see that there's not, I mean, they're similar. We analyze the product or products to be produced, determine the process required to manufacture the product, create the layout planning charts, determine the workstation. So we now go into the hierarchical process, start with the workstations, analyze the storage area requirements, establish a minimum aisle width, establish office requirement, consider personal facilities and services. We're gonna spend some time doing that in this class too. So it's not just designing for the production area, but also looking at the needs of the personnel. So how much space do you need for restrooms? How much space do you need for offices? How much space do you need for parking lot and so on? Survey plan services and provide for future expansion. In terms of the procedure based on REITs plan, we have the layout planning chart, or layout planning chart. Is the most important single phase of the entire layout process and incorporates the following: flow process, including operations, transportation, storage, and inspection, standard time for each operation, machine selection and balance, and material handling equipment. So on the next slide, I have an example of these layout planning chart. This is a summary of the operation description. So we have some figures here that are representing different things. Operations with a circle, transport with an arrow, inspection with a rectangle, delays with this, and storage with this symbol. And then based on the process that you're studying, in this case, we have the Bulele Garment Factory Process Chart. So this is for the material preparation. So we have the number, the time it takes, the proposed number and time, and the difference between the proposed and the current layout process. And then there's some details of the present methods. So basically it tells you the steps that are currently used for the operation. The details, what's happening, the method, if it is manual, and then the type of operation that is happening. So the storage, transportation, operation, and then gives you an analysis, or basically after you complete this process, you have a good understanding of where the parts or the product is spending most of the time. So for example, here, there's a lot of operation. There's 3 units of transportation or 3 steps that require transportation with 1 inspection and so on. And we also have some additional measurements for the process. So a very informative form gather you information about how this particular product is being handled through the facility. And we can build multiple layout planning charts depending on the different products that we have in the facility to gather that information as well. Okay, so using this information, we have what is called the Systematic Layout Planning Procedure, or SLP. And this is, again, systematic layout procedure methodology that was developed by Dr. Mother. The framework uses activity relationship diagrams as a foundation activity. So this is very important, so I don't want to rush through it. Still have time, have about 17 minutes. So let's look at this. It's a 10-step process. We can go back to it next time, but I want to at least give you the general ideas in which we come up with design alternatives for a facility layout. So I'm gonna go step by step, starting from the input and data and activities through the evaluation. So based on the input data and understanding of the roles and relationship between activities, material flow analysis, or front-to chart, and activity relationship analysis are performed. Okay, so those are here at the top. So front-to chart, the one that we created today for the lab, and the activity relationship chart that we also discussed today. So we start with those. So the activity relationships, here's an example. Okay, so we discussed that we have a qualitative way of stating the type of relationship between departments and then the reason behind it. So here's another example of definitions that are used for reasons behind the closeness value. So these are different from the ones you saw in the other example. So these again are based on the layout that you are trying to build. So flow of material, service, convenience, inventory control, communication, same personnel, cleanliness, flow of parts. So these are reasonings that are being used for this particular chart. These are not changing. The closeness values are the same. The rating is the same, but the reasons behind those are different. So we build the activity relationship and the flow to charts. And then we move into what is called a relationship diagram. Okay, so the relationship diagram position activities spatially. See, we don't have, what we have here is like a network, right? We have numbers. The numbers are representing the different departments. So these are the department names. And then we have these arcs that have different type of arcs. Different type of arcs. Some of them are continuous, some of them are dotted, and they have different meaning. And we're gonna talk about that now in a minute. But the idea here is that you can start seeing visually the relationship between all those departments using the information that you gather from these activity relationships and the from-to chart. Okay, so we're gonna build a relationship diagram, position activities spatially, and proximities are used to reflect the relationship between pairs of activities. So here's some coding strategy that we can use to build this type of chart. So for example, we come here and say that receiving and shipping has an A, we can build a line code for that type of relationship. AEIOUX, they have different line codes associated with them. This right here is different. So for example, we can have a bulk line like this one representing an A relationship. And then as you move down a little bit slimmer here, you have the dotted lines. Those can be representing important, ordinary, and so on. So here's a relationship diagram using that line of code. So you see very important 2 lines, especially important lines, and A4 lines. So what this is telling you visually is that if you have 4 lines between 2 and 5, is that you want to put those 2 departments as close as possible. These 2 are unimportant, 4 and 5, so you don't have to push your design to put those 2 close to each other. Same thing with these 2. But these 2, they definitely have to be close to each other. These 2, you will try to put them close as much as possible. And then as you move down, you understand you don't put as much emphasis as you move down into the rankings. So the number of lines here represent paths required to be taken in transactions between the departments. The more lines, the more interaction between the departments. Note here, departments 1 and 2 are linked together, and departments 2 and 5 are linked together by multiple lines or required transactions. So the relationship diagram position activities spatially. Proximities are typically used to reflect the relationship between the pairs of activities. So here again, we have another example. So you see, now we try to accommodate those boxes, looking at the number of lines in this case. So those that have a lot of lines together, we try to accommodate those as close as possible. And then those that are not necessarily having a lot of lines between them, they can be separated from the rest of the design. One thing that you don't account for here is the space that is needed for each department. So up to this point, we're assuming that all of them have the same space, right? So we are just looking at the relationship between them, and we are trying to organize these departments based on just the relationships. But now we move to the next step in which we have this space relationship diagram, and now we are adding the size of the departments into the figure. This gives you additional information. Like for example, if you have a constrained area, this can guide you in whether or not you can place a department in a specific location. If you put big departments close to each other, might not fit the actual design. So this is giving you additional information. So that's here, step 6. The space relationship diagram involves the determination of the amount of space to be assigned to each activity. Okay, so now you're seeing, okay, now I can see the relationships, I can see the space. So let's try to accommodate these departments as close as possible based on those relationships. And let's see if that fits our space. So based on that, we can develop some layout alternatives. So here's some examples based on this. We can come up with a design like this one. A, B, and C, you see the shape of each facility is different. So this is under the assumption that we don't have a restricted space that we need to use. If you have that freedom, then you can come up with these different designs. But if you're forcing your layout to be fit into a specific area, you might not have as much flexibility. So based on modifying considerations and practical limitations, a number of layout alternatives are developed and evaluated.